We're going to make a move now from talking about more abstract things like force vector, coordinate systems, and particles floating into space into analyzing structures and things that you'd see in your everyday life. So before we can start doing that stuff, we need to have a discussion about theoretical supports. Now, I say theoretical because these supports that we're going to talk about in theory are perfect. Like when I say a fixed support can't move, it means it can't move. In the real world, it's often impossible for us to achieve things like this. But we take the things we see in the real world and we simplify them so that we can do simple calculations. So we're going to start with supports. In this class, we're going to look at 5 different types of supports: the fixed support, the pin support, the roller support, the slider support, and the free support. Now, I have my supports organized from the most constrained to no constraint at all. So a fixed support to a free support. So a fixed support, and these supports are in 2 dimensions because we're basically going to focus on analysis in 2 dimensions. These take on more forces when we move to 3 dimensions, but that's kind of outside of the structures we're going to analyze in this. So a fixed support in 2 dimensions, and I'm going to use a kind of universal coordinate system where for all of these definitions where x goes to the right and y goes up. A fixed support can resist forces in the y direction, the x direction, and moment. So there's an x component here, a y component here, and a moment. And in 2 dimensions, this resists all the movement that you could possibly have. So a fixed support generates forces in the x, y, and a moment, and it resists translation in the x and y, and rotation. If we move from a fixed support to a spin, we move from a fixed support to a pin support, we lose the moment. A pin support can generate forces in the x and y, and obviously here I made a mistake because I labeled the forces backwards. This up and down is y, left and right is x. A pin support can generate forces in the x and y, which allows it to resist translation in the x and y. But since there is no moment there, this is free to rotate. All right? So if we wanted to come over here and lift this beam up, we can easily take it and move it from here to here without generating any force. If we tried to do the same thing with this cantilever, it wouldn't allow us to rotate here, so we'd end up bending the beam. When we move from a pin support to a roller support is just like a wheel. It can't resist forces in the x anymore, and it can only resist forces in the y. So a roller can only resist translation in the y direction. And fixed pin roller are our most common supports, and free, which is no support at all. The slider is kind of a more fun support. You see over here on the left it has wheels, so this whole thing can slide up and down in the y direction. So if you have a slider, it can generate a force in the x direction and a moment, but nothing in the y. So it can resist translation in the x and rotation. The last is the free support, which can resist nothing. It's free to move wherever it wants. These are the 5 basic supports that we're going to talk about during this class. Now, since we've talked about supports, let's talk about loads. Now, in order to have a load, you have to have something to put it on. So what I've shown here with a pin support on one side, a roller support on the other side, something spanning between the supports, and when we span supports and have loads perpendicular to it, we call it a beam. This setup is a simply supported beam that I've shown. And it is a structure we're going to learn to analyze, but not yet, but I'm using it for example so that you get used to it. So in this course, we're going to talk about 3 different loads. Point loads, which provide a load at one singular point. They can be at 90 degrees, they can be up and down, they can be at angles. Point loads are defined by P, and P has a value of force. We'll talk about uniformly distributed load. Generally, these are a line with arrows pointing down. They are defined by W, which has units of force per length. Now, in order for us to do any type of analysis or with this uniform load, we need to find the resultant of the force. So for a rectangular load, the resultant occurs in the middle and is equal to W times L. The most complex load we're going to look at is the triangular load. Now, the triangular load is usually defined at its peak or its highest point by P, but in this case, P again has units of force per length. In order to work with it, we need to find this resultant. The resultant for a triangular load is 1/2 E times L, or the area of a triangle, and it is not located at L anymore. It is located at, write it down to the bottom, 2/3 L from the skinny end, or 1/3 L from the fat end. In order for us to work with any of these distributed forces, be it uniformly distributed or triangular, we need to find the resultant force. Now, let's talk about equilibrium. If something is in static equilibrium, it means that every portion of the beam is not moving. So for something to be in static equilibrium, it needs to be in external equilibrium and it needs to be in internal equilibrium. External equilibrium is based on supports or boundary conditions. Different supports give different boundary conditions. So I'm going to go back to the simply supported beam. I have some set of random loads on top, and I have a pin and a roller. We said pins give us forces in the X and the Y direction, and the roller gives us only a force in the Y direction. So here we have 3 forces which match up to our 3 equations of equilibrium. In order for something to be in equilibrium, externally, the forces and the supports have to equal 0. The forces and the forces from the supports have to equal 0. That will put it in external equilibrium. Internal equilibrium also must hold. Internal equilibrium is based on loading and structural type. Now, this is where I bring in another important tool of statics, which is called the section cut. Because anywhere that we look at a structure and we cut it and look internally, we have internal forces. Depending on how the loads are carried, the internal forces change and the requirements for equilibrium change. So when you make a section cut, you basically break a structure apart at a random point. So I'm going to cut between this force and this force. Let me draw for you the broken part beam scale. Now, if we look here, we have forces acting in the y. These two act exclusively in the y. This is at an angle, so it acts in both the x and y. Internally, each of these pieces we look at, so I'm going to look at the right-hand side. When we make a cut and we look at the forces internal to the beam and the external support, all these forces still need to be in equilibrium. So we have to have forces in the y direction. We have to have forces in the x direction. And we also, since there's forces and distances, have to have moment equilibrium. Now, for these internal forces to be present, it's a condition of the beam or the structure we have. So internally, not everything can resist forces x, y, and moment. So one of the first structures we're going to learn to analyze is a cable structure. And a cable structure is special because if this green line was a cable, it could not resist forces in the y or moment. So it's basically a function of what the thing is made of and how the loads are applied. When we look internally, while these forces are acting in the x and y direction, they have different names. So moment is always called moment. Forces acting along or parallel to a member are called axial forces. And forces acting perpendicular to a member are called shear forces. And we often simplify this as M, B, A. Now, these internal forces, shear and axial, and the internal moment have to be equal to the externally applied loads and the supports. There has to be equilibrium between the internal forces and the external forces. When we make a section cut, we reveal those internal forces, and we can use our three equations of equilibrium to evaluate those forces. So based on our supports and our structure types, we need to make sure everything in statics meets both external and internal equilibrium. We're going to ensure this by using our equations of equilibrium. And that is all the tools and all the things you need to do the rest of the course.